We're asked to create the power series for the derivative of f. And so what we can do is we can look at each individual term and differentiate it. We're looking for f prime of x, which means we want the derivative with respect to x of n equals 0 to infinity, because this series is equivalent to this function. Right? So finding the derivative of each term in the series is equivalent to finding the derivative of the function. So if we do that, the derivative with respect to x of x to the 3n, the first term, if you plug in n equals 0, you get 1. If you plug in n equals 1, you get x to the 3rd. If you plug in n equals 2, you get x to the 6th. Plug in n equals 3, you get x to the 9th, etc. So if we differentiate each term, we get 0 here, 3x squared, 6x to the 5th, and then we get 9x to the 8th. So a pattern is forming, and we can use that pattern to help us create the series. The powers are going up by 3 every time, and then the coefficients are multiples of 3. So the derivative of f as a power series could be the sum from n equals 0 to infinity of 3 times n, right? Because when n equals 1, we've got 3. When n equals 2, we've got 6. When n equals 3, we've got 9. So that takes care of the coefficients. And then it's going to be x to the power of, well, when n equals 1, we need to have a 2 here. So we could say 3n minus 1 for a power. Let's see if that works. If you plug in n equals 2, we're supposed to have a power of 5. So 3 times 2 makes 6. 6 minus 1 makes 5. Checks out. Okay, and that's it. So it's really about expanding, differentiate each term, expand, and then eventually see a power to represent the derivative of that, the power series for the derivative, I should say.